and welcome back. Now let's see if we can figure out what we can do to fix 1's complement. Is there anything we can do? And guess what? It's called 2's complement. We'll also talk about something called biased encoding. So here's the idea. The problem is the negative numbers overlap with the positive numbers. We saw that. We don't want that. We want to shift the bottom over 1. So here's what we do. Just like before, all the zeros are on the top. So like in the 5 bits before, all zeros up to 0, 1, 1, 1, 1, 1. That's all on the top. That's 0 through 15. That's the same. So it turns out the top never really changes. Doesn't change. Actually, 0 to all 1s doesn't change in unsigned, signed magnitude, 1's complement, or this 2's complement. So that's kind of, the top stays the same. It's what happens on the bottom. Except all 1s, we don't want it to be 0. We want all 1s to be -1. And in fact, I want you to lock that in. All 1s is always -1s in this 2's complement number. Okay? It's called 2's complement. The hardware is now really, really, really easy. We went from being complicated, because these 2 zeros, to really easy, actually. By the way, if you're a C programmer, we'll teach you in this next lecture, you're going to see that in C it's called an int. Again, we don't know how wide ints are, so we had this thing called int types. We'll tell you int, int, I for integer, int with a number, 8, 16, or 64, 8, 16, 32, 64, etc., is a signed integer, and this is 2's complement. So whenever you think of a signed integer, the sign means we're doing this 2's complement signing to be able to handle negative numbers. Okay? Unsigned means only positive numbers or only non-negatives, 0 or positive numbers. Okay, here's the formula. Here's the way to think of it. Okay, so for 32 bits, the same as before. All the lower bits are the same, right? The lowest coefficient times 1. The second lowest bit times 2. The third lowest bit times 4, etc. Except that you take this big guy and you say it's multiplied the coefficient, whatever the higher bit is. It's that kind of that sign bit, really. It's not really a sign bit because it's not sign magnitude, but we think about it as a sign bit because the negative numbers all have a 1 there. So we'll think about it as a sign bit for this case, even though it's not sign magnitude. Times minus 2 to the 31. Minus 2 to the biggest term. So let's do this. Simple. Let's go back to a nibble now. Not 5 bits. Go back to a nibble. 4 bits. 1101. Well, 1101 in unsigned, well, in hex, 1101 is D. Memorize that guy. Okay? D. That was going to be 13. What is it if we're talking about 2's complement or a signed number, 2's complement? Let's do it again. Well, this is 101. So this is that's 2, no 1, 4, no 2, 1, 1. And this is -8. So watch this. Here's your 5. Remember, 101 is 5. Minus 8, there's -3. Okay, that's one way to think about it, -3. Another way to think about it is flip the bits and add 1, and that's the equivalent number positively. So let's do this. Let's flip the bits and add 1. So here we go. 1101. Flip the bits. 0010. Add 1. 0011. That's the negative of it. So if that's a positive number now, it's 3. That means 1101 must have been -3. Let's do that. Let's reverse it now. Flip the bits again. 1100. Add 1. 1101. And that's -3. So I went from -3 to 3 to -3. By the way, this picture is an optical illusion. Some people see a vase, some people see a face, sometimes it flops between a vase and a face. The point of that showing you this is I can think of this the way I do it, the way, as a pro tip, the way that I think about negative numbers and how to do them fast is I actually see, when I say, okay, this leading 1 now, I immediately see this and I flip, I treat every one as a 0 and a 0, 1, which means I basically do this in my head, okay? And then I just quickly add 1 and I say it's to be -3. So I say to myself, oh, here's this. Now, if this is the only one, and I add 1, it's -3. See that? Because I quickly flipped it, thinking that's the only one, and if I add 1 to that, I get 011, and then I go back and I say, what's that in decimal? It's 3. So I'm able to do that really fast. Think about how to do that fast for yourself. So, flip the bits and add 1. So here we got a number line, this beautiful number line. As I count around, as I'm counting around here, in my binary odometer, I've taken my odometer and kind of made it round. Here's the numbers that are being represented as I do this. 0, 1, 2, 3, up to 15. This is the same. This is always the same. Just like the positive numbers are always the same, 0 through 15. It's been that way for every representation we've seen so far. All zeros through 0 and all ones is 0 through, here in case 15 for 5 bits. Then it jumps to minus 16. Jumps to minus 16. And you might remember this last slide. Watch this slide here. Remember this? This is the negative number. That's this minus 8 that pulls it back. By doing minus 16, it took this representation, which used to be in one's complement minus 15, and then all the ones was here. We didn't want that. We wanted to bring it back one more. So that's why that term, that top level term, minus 16, pulls that down so that this is the minus 16, pulling that value down to minus 16. If I then stretch 16 more guys or 16 more guys there, this will end up at minus 1, right? Minus 16 to minus 1 is 16 things. So that's why that works, that cool top level term. This cool top level term, it's because you grab that negative guy, that smallest negative number, and pulled it over by exactly 1. In one's complement it was minus 15, and now it's minus 16, which is why it works. So let's look at our odometer now, and let's see if let's see if our overlap here. Ready? There we go. There's 0 to 15, and no overlap. And as I said before, all ones is negative 1. Huh? With the thing and the negative is all ones negative 1. Love it. Okay. 2 to the n minus 1 non-negatives, 2 to the n minus 1 negatives, 1 0. Okay. How many positives? Ask yourself that. And then we'll see this next encoding, which is called the biased encoding. Now, one of the things that's interesting is none of these guys had negative numbers they could represent, but also all zeros being the smallest value. Here's an analogy for you. I'm recording some electrical signal. Okay, I'm recording some electrical signal, and it's wavering from 0 volts, which is let's say it's a DC voltage, to 31 volts. Okay, and I'm going between that. So nothing there, and now it goes to 31, and it goes down to there, and I want to have 31 different representations in there. Well, let's say it's wiggling like this. If you think about graphing this, it'd be a graph that's always a positive thing. And I said to myself, wouldn't it be cool to kind of grab this graph and just bring it down so it wiggles around 0? That's what this does. It takes these values and pulls them down by some bias. To add an offset, we call it a DC bias, it will, if I add minus 15 volts, then now all of a sudden my signal is wiggling down here across 0. So this bias brings things down so it's kind of balanced across 0. But now you see the problem is, 0 is one guy, you're never going to have an equal number of positives and negatives because that's a total of, like 0 is one thing. Either you have 2 zeros and then an equal number of positives and negatives, or you have 1 0, which was what we want, and then an unequal number of positive negatives. And if you recall, I have one more negative than positive in a 2's complement representation, right? I only go to 15, but I go to minus 16 as my biggest negative, okay? In bias, we're going to take my numbers, my unsigned numbers, 0 through 31, and then add this bias on top of it. Pulls it down. And what distinguishes it from that, I could either add minus 16 to it, so they're almost exactly the same as the 2's complement. That's not what we do, what we typically do. So by default, we're going to have a bias chosen as minus 2 to the n minus 1 minus 1, meaning I got 5 bits here, make it 4 bits. 2 to the 4 is 16, subtract by 1 is 15, minus 15. That's my bias here, okay? So if I grab all 0, here's the unsigned. Remember, look, unsigned. Pretend this is unsigned, okay? Unsigned, all zeros to all 1, in that order. If I grab it and shift it back by minus 15, what I get is all zeros is now the smallest negative number. And it just keeps counting up. 1, 1, 1, 1, 1, 1. It's actually beautiful this way. Here's my odometer. It just does the right thing. So I start with the smallest negative number, which again is this value here. And I just keep going up by 1. And nothing strange happens around 0. I just keep incrementing. Minus 1, 1. Nothing strange happens there. Unlike before, where it would snap around, it would wrap and flip. No, it just continues to count up. It just works. You can think about, by the way, 0, this is actually the equivalent of the bias. When minus 15 adds to the unsigned value 15, I get 0, because the number is the unsigned value plus the bias. Okay? It'll take some practice. but we really like biased encoding for some applications, and we'll see that actually later in this course. And in summary, we're at the finish line, woo! We represent things in computers as bit patterns. N bits is 2 to the n things. We've talked about 5 integer encodings. Each of them have benefits, and each of them have shortcomings. One's complement and side magnitude have the most problems, so we don't use those. What we typically use is the remaining 3. We use unsigned, 2's complement, and bias. We're going to see those guys. Unsigned comes for free in a programming language. Here we go. Unsigned numbers are uint in C. 2's complement come as ints, or int n underscore t. Biased, there is no way to do that. You have to almost store the bias together or remember that, and if I'm shipping you some bits, I'll ship you an unsigned, and then I'll encode it as, for example, if I'm going to store 0 through 31, let's say I'm going to store some numbers, like let's say minus 6, oh, here we go, minus 16, minus 16, minus, let's go back, minus 15 to 16. Okay, I want to store that number. I want to store this. How can I give this to you if you and I are agreeing on this? There's no way in the computer to do this, but you and I are agreeing on it. What we do is I send you mail saying, P.S., the bias is going to be minus 15. And then I hand you the unsigned value. So I take my number from minus 15 to 16. Okay? I add back the bias to find out what the bit pattern is. Okay? All right, maybe I should. So now I have 0 to 31. I encode that as a number 0 to 31, I ship it to you, you apply the bias, and now it goes back to the range that I had. So I had a number from minus 15 to 16, I convert it to the unsigned equivalent of it, give it to you, and then you decode that. That's the way you have to do biased. Overflow is when it wraps and the bits aren't enough to store the actual number that you want, because numbers are infinite, but the numerals and the space we have is a finite value. You saw this ain't no free lunch. To get negative numbers, we had to steal something from the positive space. We now couldn't go to 31, we only could go to 15. And you saw all of them actually able to go to 15, except for bias, which goes to 16. Meta takeaway from the big picture is we often make design decisions to make the hardware simple. And one of the reasons we threw out sine magnitude and 1's complement is that the hardware to build that would have been really hard. But the hardware to build unsigned and side magnitude is really easy. And in fact, I'll give you a secret as we start. This is like I'm foreshadowing probably 10 weeks ahead. It's the same hardware. It's the same hardware to do mathematics on unsigned and 2's complement numbers. The only thing you have to worry about is overflow, because different things overflow, because the ranges are different, right? The ranges, this is 31, and this is, you can do something weird. You could overflow negative there. It's a little different for the overflow calculation, but the rest of it's exactly the same. So it's really cool. You can use the same hardware to add 2's complement numbers as you could to add 2 unsigned numbers, if you don't care about overflow. That's pretty cool. That's the end of this lecture on number representation, folks. It was really fun. The next module will be a series of lectures on C programming. I'll see you there.